Hello, in this video we want to discuss the parallel axis theorem. So this is our setup. We have a rigid body and its center of mass is C. We have point A on the rigid body, it's just a material point on the rigid body. And say that I know the components of the inertia, the moments of inertia and the products of inertia about C. Now to calculate the moments of inertia about A, where the axes are parallel, meaning that if I have say Ex, Ey, Ez at C, then Ex, Ey, Ez at A are parallel. If I want to calculate the moments of inertia and the products of inertia about point A, about point A, do I need to do the integrals all over again, or is there a shortcut I can take? So remember, the products of inertia about point C, for example, ICZZ is the integral over the body of x squared plus y squared dm. So for every mass, we're considering its distance from the ZZ axis. Excuse me. That passes through the center of mass. Remember the position vector of dm minus or relative to the center of mass C is xex plus yey plus zez. Now, point A, I will write the position vector RA minus RC, the position of A relative to the center of mass, as AXEX plus AYEY plus AZEZ. Now, when I calculate the moments of inertia about A, so this has to do with the mass distribution about or from the ZZ axis passing by A. So let's think about that for a little bit. That's gonna be equal to the x and y component of R minus RA. What is R minus RA? Well, that's R minus RC minus R, or actually minus RA minus RC. So that's equal to x minus ax ex plus y minus ay ey plus z minus az ez. So the moment of inertia IAZZ, which has to do with the mass distribution about the ZZ axis passing through point A, is going to be equal to the integral of x minus ax squared plus y minus ay squared tm over the body. So let's skip these and continue with this calculation. That's the integral over b. I can expand the square to get x squared plus y squared dm plus the integral of ax squared plus ay squared dm plus the product plus the integral to ax, and I think that's a minus sign outside, minus 2ax times x minus or plus ay times y dm. Now this first integral is none other than ICZZ. The second one, I can take ax and ay outside. They do not depend on tm. So that's just equal to the total mass times ax squared plus ay squared. And that's IAZZ plus that term, the minus 2, the integral. I'll divide it into two integrals actually. That's minus 2, and then ax, the integral of x dm over the body, plus ay, the integral of y dm over the body. Now these two integrals are going to be equal to 0. Why? Because remember, the integral of r minus rc dm is equal to, over the body, is equal to the integral of r dm minus rc, the integral of dm, which is just 0, because this is by definition rc times the total mass, and that's the total mass. This is also equal to the integral over the body of x ex plus y ey plus z ez dm. So that's the integral of x dm along ex. So the ex does not depend on the material point on the body, it depends on the rigid body as a whole, so we can take it outside the integral. Ex does not depend on dm. Same for ey and ez. Integral of the body of y dm plus ey plus the integral over the body of z dm ez. That's equal to 0 vector. So if I project this equation along ex, I'll get that the integral over the body of x dm is equal to 0, and same if I project along ey and if I project along ez. Okay, so if these two terms are 0, then our parallel axis theorem is this one. That's the parallel axis theorem for the moments of inertia. Analogous expressions hold for the other product of moments of inertia. For example, a yy is equal to ic yy plus the mass times ax squared plus ac squared. The proof is exactly the same as this one. Remember, the parallel axis theorem can only be applied between the center of mass and some other point where the axes are parallel. The center of mass always needs to be here. We cannot put any other random point. That's because this term only becomes 0 if x and y are measured from the center of mass. Now what about the parallel axis theorem for the products of inertia? For the products of inertia, well, let us see. I c x z, for example, is the integral minus xz dm over the body. Let's double check this. I'll scroll up and to the expressions we found for the products of inertia. Yep, this expression here matches up with what we just wrote. Very well. Now for the product of inertia about A, this has to do with the mass distribution about the n-axis or the axis passing through A. So instead of x, we're going to have an x minus ax. Instead of z, we're going to have a z minus az dm over the body. I'm going to multiply this out. xz dm minus the integral of ax az dm over the body and minus ax times z dm minus az times x dm. I hope I don't have any calculation mistakes here. So this first term is none other than the ICXC. This one, we can take the AX AZ outside, and that's just the total mass times AX AZ. And I think you can show that these two terms are equal to 0. So you'll get that IAXZ is ICXC minus the total mass times AX AZ. And that's the parallel axis theorem for the products of inertia.